And now to discuss the moon. Topics we will cover include lunar cycles, our moon, and satellite systems and rings. As you know, the moon takes almost a month to make one cycle in orbit around the Earth. From the Earth, we see the same side of the moon. However, we do not really have what is called a dark side of the moon. All parts of the moon receive sunshine at some point during their orbit. Occasionally, the moon ends up being right between the Earth and the Sun, blocking out the sunlight to Earth. This is what is known as a solar eclipse. Incidentally, the picture here you see that says what you see from Earth is what you would see if you could look directly at a solar eclipse, but it is inadvisable to actually look directly at a solar eclipse. It could damage your eyes. The darkest part of the eclipse is called the umbra. The area surrounding that is called the penumbra. Here's a map showing the path of solar eclipses that will take place during different times. It looks like the next one is in March of 2016. This will be in Southeast Asia and the Pacific. Will not be visible from our vantage point. However, in 2024, it seems that we have a good chance of being able to spot a solar eclipse if we travel a little farther north from our location here in western Pennsylvania. Another kind of eclipse that can occur is when the Earth gets in between the Sun and the Moon. This causes what is known as a lunar eclipse. What happens is that the light from the Sun goes through the edge of our atmosphere, giving the Moon an orangish reddish glow. Picture what you see at sunrise and sunset. When the sun is low in the horizon, it has that distinct orangish color that is cast. Sunlight going through the atmosphere and lighting up the moon this way gives it a similar shade. Similarly to a solar eclipse, there is what is known as the umbra and the penumbra. You may wonder to yourself why eclipses don't occur every time the moon is in position where it is between the sun and the earth, or every time the earth is in a position where it is between the moon and the sun. This is because the plane that we orbit the sun on is slightly different from the plane that the moon orbits the earth in. The lunar earth plane is tilted at an angle of about 5 degrees compared to the plane that we orbit the sun. This means that in most cases, the moon passes right through, or the earth passes right through without a shadow being cast on one another. The timing has to be just right for an eclipse to occur. And now a more detailed look at our moon. The moon is very prominent in the sky and is often one of the first things that beginning astronomers look at to view. Even with a modest telescope, or even with your naked eye, you can see that the consistency of the surface of the moon is not uniform. A closer look reveals craters where impacts have occurred, and smooth darker regions known as maria, and more grayish regions which are called highlands. Craters are signs of impacts that have occurred. There are so many craters upon the moon that sometimes we see craters within craters. You may wonder to yourself, if the moon is our closest object in space, why don't we see so many craters on the Earth? The fact is that impacts occur on Earth with at least as much frequency as they occur on the moon. But on the Earth we have weathering and other geological forces that act to erase these craters from the surface of the Earth. The moon, on the other hand, experiences no such weathering patterns or geologic activity. The highlands are regions of mountainous area that are formed of lower density rock. The maria, on the other hand, are darker. They were formed from seas of molten rock cooling. The question on this slide is very important. The far side of the moon is not the moon we are used to seeing. You probably were able to identify this as being the right picture. This side of the moon is hidden from our view, however, it is not hidden from the sun. It is not the dark side of the moon. It experiences light, specifically when we have a new moon, and the side that we're used to seeing face us is dark. That's when the far side is light. In fact, the idea of the dark side of the moon is actually a misnomer. There's no such thing as the dark side of the moon, where there is a place that is in perpetual darkness. There's no place on the moon that it doesn't receive sunshine during some part of its orbit. There are other features on the moon if you look carefully. Some are known as rills, look like little lines or pipes. They're thought to be ancient lava tubes. Some craters exhibit central peaks. These indicate a very large impact where material was thrown up. Here's a cartoon illustrating how maria were thought to form. A large asteroid would impact the moon, creating a huge basin. Since this happened early in the moon's history, there was much lava not far beneath its surface. This molten rock filled in the basin, then later cooled to leave the maria behind. The moon was studied by astronauts directly. They used seismometers to figure out a little bit about what the interior of the moon is like. It's thought to have a similar iron core to the Earth, slightly off-center, the crust being thinner on one side than on the other. The moon has a very thin atmosphere. It is practically non-detectable. No atmosphere means no weather, however, so things like the cratering are left for us to see today, even if they happened long ago. Similarly, the footprints left by the Apollo astronauts should be there for a long time into the future. This cartoon illustrates how the moon actually turns on its axis. It is in sync with the motion of the Earth, which is why we see the same side of the moon at all points during its orbit. But if you could picture the sun, let's say it's located, for this example, where the text is located on your slide, and is shining to the left of the Earth-Moon, towards the Earth-Moon system, then at point A, the sun would be shining on the mountain that you see, facing the Earth. But at point B, the sun will be shining on the exact opposite side of the moon. This further illustrates that there is no part of the moon which does not receive sunshine at some point during its orbit. Again, there is no quote-unquote dark side of the moon. The best explanation for how the moon formed is via a huge impact. Make no mistake, this is not an asteroid we are talking about, nor a comet. We are talking about, very early in the history of the solar system, what is known as a planetesimal, a planet-like object nearly the size of Mars, impacted the young Earth. This devastating impact caused debris to be ejected from the Earth. This debris swirled around the Earth and eventually cooled and congealed to form the moon. This explains both why the moon is similar in composition but not exactly like the same composition as the Earth. This computer simulation demonstrates that such an impacting planet on the young Earth could form a moon in such a way. Notice the time scale involved. It did not take long for this cataclysmic event to occur. Earth is not the only planet to have moons. Generically, we call these moons satellites. Rings are similar in that they are comprised of many particles in orbit around a particular planet. The first moons that were known, aside from our own, were what are called the Galilean moons. They are the 4 largest moons of the planet Jupiter. and as the name implies, they were discovered by Galileo. At first he didn't know what he was seeing, but over time he tracked the motion of the 4 specks of light he saw near Jupiter. From their positions, he was able to deduce that they were gravitationally bound to Jupiter and were therefore some kind of moon. Even with a small telescope, you can see the Galilean moons. My own 4-inch telescope at home is sufficiently big enough to see all 4 Galilean moons. And other planets in our solar system also have moons. Some of them are very big. The Earth's moon is shown on this diagram for comparison. And you see that some of the moons of our solar system are even larger than our own moon, for example, Ganymede and Titan. And they all have very interesting properties, some of them being particularly noteworthy. Triton, for example, has volcanoes of ice. Titan, Saturn's moon, on the other hand, has a very thick atmosphere. It is the only moon known to have a significant atmosphere. Io has active volcanoes, and Europa has ice which is thought to cover a liquid sea. The Galilean moons are the ones on the left of this diagram, marked as Jupiter's moons. And then you see Titan and Triton to the right of those. Io, Europa, Ganymede, and Callisto are the names of the Galilean moons. A mnemonic to help you remember the order, if you're curious, is I eat green cheese. Iapetus is one of Saturn's moons, and it is very strange in appearance, having one side which is very light in color and the other side very dark. Enceladus, another moon of Saturn, is noteworthy for the geysers of ice which have been seen ejecting water into space. Uranus's moon Miranda appears to have been shattered and reformed, possibly due to an impact. Or another idea is due to tectonic activity. The cliffs you see here on Miranda are 20 kilometers tall, which is about 12.5 miles. Saturn is what we think of when we think of ring systems. Galileo observed that Saturn had these rings, but he did not really understand what they were. Over time, people were wondering whether the rings were solid or comprised of particles. Maxwell hypothesized that they could not be particles, but rather, theoretically, they should be... Maxwell hypothesized that they were not solid, but in theory, they ought to be made up of small particles. But it was James Keeler at the Allegheny Observatory here in Pittsburgh who was able to demonstrate without a doubt that this was the case. He used the telescope pictured here, the Fitz-Clark telescope, to observe the Doppler shift of different parts of the rings. Recall again that the Doppler shift is when light appears redder or bluer than we think it should, based on its motion towards us or away from us. A red shift would indicate an object is moving away from us, whereas a blue shift would indicate that an object is moving towards us. Keeler understood that if the rings were moving as a solid, like a record, that their motion ought to correspond to the following relation, V equals R omega, which relates the angular velocity and the distance of the particles from Saturn to their linear speed, which he could detect from his Doppler shift. On the other hand, if the velocity implied by the Doppler shift followed a different relation, specifically that of a Keplerian orbit of a square root of g m over r, then this would indicate that the rings were comprised of small particles, each traveling with this specific velocity. The Doppler shifts observed by Keeler implied a velocity that held only for the case of Keplerian motion, which implied that the rings must be made of smaller particles, as Maxwell hypothesized. A closer look at Saturn's rings reveals that they are comprised of many tiny ringlets. There are gaps in these ringlets, such as the Cassini and Encke divisions. But other planets also have ring systems. Jupiter has a thin ring, as does Uranus and Neptune. It is thought that the thin ringlets are maintained by the action of shepherding satellites, which gravitationally keeps the rings in line.